Hi, today we are going to use the ResNet50 deep learning network in order to classify between alien and predator. So we are going to take several hundreds of images from the predator movie and the alien movie, and we will do a transfer learning of the ResNet50 network in order to classify between those two categories. So this is the link for the Kaggle dataset. As you can see, these are the alien images, and also we have a predator images. All the images are divided to a train and a test dataset. So we will download the images locally, and we will start coding our model, our transfer learning model. As you can see, these are the images. Each image is in a different size, so we are going to resize all the images for our model. So let's start. The first Python code will be loading the data and building the model, and also training our new and fresh model. So let's start with the import process. We will import the necessary libraries for deep learning operations, data handling, and visualization. We will use TensorFlow and Keras. These will be our building blocks for the model and the training. And we also use NumPy for numerical computations. And let's also use the globe library for path operations, and we will also use the matplotlib in order to build a diagram and see how well our training progress. So as you can see, these are the Keras libraries. We are loading the ResNet library, and also some Keras layers like the dense layer, the flatten, and also the model. We are going to build our customized model, and as I mentioned earlier, also NumPy, globe, and matplotlib. Okay, let's continue. This will be our PLT library. So now we are going to define the image size. We will specify a size of the input images. The input images processing as 224 by 224 pixels. We will define the train my images folder and the test my images folder variables, and these variables will contain the path for the directories containing the training and the testing image dataset. Then we will start the model definition. We will load the ResNet model. This pre-trained model with ImageNet has the ability to classify 1000 images, but we are going to chop our top layer by using the argument include top false. This will help us and give us the ability to add our own layers and define our own two classes, the predator and the alien. Okay, let's run it. So this is the ResNet50 model out of the box. Just double check that it was loaded correctly, and let's continue. Now we will freeze the model weights. Since the model was already trained on the ImageNet, we would like to use the existing weights, so we are using the layer.trainable equals false. Now we will obtain our classes. We will use the globe function in order to obtain the list of classes. Basically we have only two, but we will load the name of the classes out of the folder names. Each directory represents a different class of images, so the list of classes will be stored in the classes variables. And also the number of classes, we will get the length of the classes list in order to determine the number of classes in each dataset. Let's run it. As you can see, these are the two folder names, which are basically the two classes. Now let's continue with building our model. We will add layers on the top of the pre-trained ResNet50 base to build our classification model that will be named model as the end of this build. We will add a global average pooling layer. This will add to reduce the spatial dimensions of the features. Then we are going to add one moment. Now we are going to add a flatten layer, and the flatten layer is added in order to convert the output of the global average pooling into a one-dimension tensor. And next we are going to add our dense prediction layer, and we will use, of course, the number of classes, which are basically 2 classes. So this will be the number of classified classes, and we will use the softmax activation for a multi-class classification. We can also use the segment as a binary since there are only 2 classes, but as for this example we will use the softmax. Then we will merge everything together. The model class is used to define the input and the outputs of the model, and at last this model variable will print the summary of this model just to see that everything was defined correctly, and we are expecting to see as last layer with 2 classes. Right. And also you can see that the trainable parameters is about 4,000 parameters. All the rest, of course, are freezed, and we are going to use the existing weights. Next, we are going to compile our model. We will use, of course, a categorical cross entropy since there are several categories. And we will also use the Adam optimizer. We define it with a learning rate of 0.01, and the evaluation will be based on our accuracy. Great. Let's continue. Now we will use some data augmentation in order to enlarge our model. We will prepare data generators for training and for testing, and we will use it in order to load our dataset. And on this data generator we will use some data augmentation. For example, we are going to do some zooming on the imaging and some horizontal flip in order to enlarge our dataset. And of course we are going to normalize the data between 0 and 1 by dividing all the pixels by 255. As for the dataset, we don't need augmentation, only normalize the data between 0 and 1. And now it's a time to load our data. So we will, as for the training set, we will use the train data generator, and we will use the flow from directory function, and we will send several arguments. First, the name of the train images folder, then the target size. We would like to load the data and convert it at once to 224 by 224. The batch size will be 32. That means each 32 images will be accumulated in one batch, and the closed mode will be categorical. We will do the same with the test data generator and the test dataset. Great, let's continue to the next step. Now let's define the total number of epochs. It will be 200. Basically we will add early stopping, so we will not run through all the epochs. And let's define the best model file. That means that each time the model will improve during the training, it will be stored in this file, alien predator model.h5. Now let's define our callbacks. So the first one will be the model checkpoints. This callback saves the model weights after every epoch if certain conditions are met. So basically we are expecting that each time the model was improved and we have a better validation accuracy, we would like that the new weights will be stored in our .h5 file. The next one is the reduced on plateau. This callback reduces the learning rate when the matrix has stopped improving. So the patience is the number of epochs where with no improvement after which learning rate will be reduced, and the factor is what will be the factor, the new factor for the change of the learning rate. And basically we will duplicate the factor with the learning rate in order to create a new one. And the early stopping, this callback stops the training when the monitoring matrix has stopped improving. So in this time the patience will be 30 epochs. Now this is the training process. We will use the Feit function in order to do all the training. We will send several arguments, the training set, which are all the images of the training, the validation data. These are all the images, all the data set that we loaded earlier, the epochs, which is 200, and also how many steps per epoch and the validation step. You can see this is the process in order to calculate it. We will also send the arguments of the callback that we defined earlier. So after the training, we would like to detect what is the best validation accuracy. So we will get the max out of the history results, and let's print the best validation accuracy, and this will be this value best val ACC. And the last process will be plotting a diagram, and we would like to show all the epochs, all the history epochs after the training. And basically we would like to demonstrate two diagrams. One will be for the accuracy, and we would like to print the training accuracy and the validation accuracy, and to see if they are on the same direction. We're expecting that this graph would go up, on the direction of up. And the second diagram would be the loss, and we will follow the loss and the validation loss as well. So after this process we are ready to run our first Python program. So let's run it. I have a syntax error. It should be categorical. Probably have a syntax problem. Yes, let's add the E and let's run it again. Okay, these are the number of the images for the test and the train, and the training has started. As you can see, each time the training has better results, it saves it to our .h5, and if not, the results is stay. The best one will be stored as the previous results. So we are not going to wait until all the 200 epochs. Let's jump directly to the last one. So this is the training diagram. As you can see, there is a correlation between the training accuracy and the validation accuracy. The training was about 70 epochs. Let's also follow the loss. This is the training loss and the validation loss. Once again, the same correlation, so very good results. And now we are ready to test our model with a new and fresh image. So first of all, let's see our test images. We have one test image for the alien and one test image for the predator. I will also add these test images to my code, and I will leave the code. I will leave a link in the video description for this code and for these two images as well. So let's start with the import TensorFlow library, and then we also import in OpenCV and OS module for interaction with the operation system. And next we will upload or import some Keras utilities for dealing with the image and manipulation. Also, we will import a NumPy, and now we are ready to start. Yes, of course, it's step number 2. So let's copy some of our previous code. Let's copy the path for our training images, and let's load the name of the classes, and also let's get our number of classes. Basically it's 2 classes. What else? We would like to copy the name of our best model file. I believe that's it. Let's start with loading our pre-trained model from the specific file path. We will use the load model function for that. And now let's define the function to prepare the image for the prediction. So this function would load the image from the given file path and resize it to our specific dimensions. Then we will convert the image to an array representation. Now we will add an extra dimension to the array to make it compatible with our model input. It expects a batch of images, so we are creating a batch with only one image inside it. Now we will normalize the image pixel values between 0 and 1, and then we will return the prepared image array. Now let's specify the file path for our test image. Let's copy the relative path. Let's change the directions of the slashes. Now we will read the test image using OpenCV functions, the imread. Let's run our function in order to prepare image for prediction. And next we can run the prediction. Okay, this predict function will return the probabilities for the test image. Let's print the predicted class probability array. Let's run it. As you can see, in a few seconds there are 2 values, one for each of the classes. One has a value of 0.2 and the other one 0.7. That means that 0.7 perhaps is our predicted class. So let's get the index of the predicted value. Before getting the index, let's get the highest answer, the highest predicted value. We will use the argmax for that. Let's print the answer. So we're expecting to see 0 or 1 since we have 2 categories. So this one is 1. So what is this one value? In order to do that, we would like to get the class name out of the class index. So we will use the classes list, and once again let's print the class name after the prediction. So basically we are retrieving the class name out of the list by the index. So this predicted class is predator. So this is correct. As you can see, it's a test predator image. Now let's add the text, the class name. Let's add it to our original image. We will use the putText function for that. And basically we are expecting to see our original test image with the name of the class, the predicted class name. Let's use the imShow in order to display the image, and let's run it again. As you can see in green text, this is the predator. Let's put the text in the center of the top image. Let's run it again. Okay, now it's a better place. As you can see, predator. Now let's test the other image, our alien image. This one. Let's copy the path for our image and let's run the same prediction and test it. Great, as you can see, it's an alien. Thank you very much. You are most welcome to subscribe my channel. I hope you enjoyed this tutorial. Bye bye.